In 1935, three minds, Einstein, Podolsky, and Rosen, sat uneasily at the edge of quantum dawn. They proposed a thought experiment meant to expose an incompleteness in Schrödinger's strange new map. Two particles spring from a single source, momentum balanced like skaters pushing apart on frictionless ice. Measure one far away, and, in that instant, you deduce the other's momentum without touching it. Einstein called the implied connection spooky action at a distance. Either information travels faster than light, violating relativity, or quantum mechanics fails to tell the whole story. He wagered on hidden variables, secret settings carried at birth, quietly scripting each particle's reply to future questions. If such variables exist, correlations between distant results can never exceed a certain classical ceiling. The EPR paper was more than criticism, it was a gauntlet. Either reveal the concealed gears of reality, or accept that measurement here can instantaneously reshape potential there despite oceans of vacuum between. For decades, the question lingered, an unresolved debate carved into footnotes until a Northern Irish physicist converted philosophy into an experimentally testable inequality. John Bell, tinkering after hours at CERN in 1964, translated EPR's debate into a game of statistics. Picture Alice and Bob at opposite ends of the galaxy, each with a detector that can be set to one of two angles. They measure entangled photons and record outcomes as bits, +1 or -1. Classical hidden variables predict that, averaged over many runs. Certain combinations of correlations now wrapped into the CHSH inequality can rise no higher than 2. Quantum mechanics, in contrast, forecasts a larger wave-like correlation. Multiply Alice's and Bob's bits, add and subtract in the right pattern, and you obtain 2 square roots of 2 approximately equals 2.8 to 8, a clear breach of the classical ceiling. Crucially, this prediction does not require faster-than-light signaling. The spooky link lives in the shared quantum draft written before the particles parted. Bell's inequality offered experimenters a lights-on scoreboard. Violate the bound and hidden variable realism falls. Early tests in the 1970s suggested quantum victory but left loopholes such as detectors too slow and settings chosen in advance. The stage was set for a new generation of experiments that would fire photons, flip random coins at nanosecond speed, and finally decide whether the universe keeps private ledgers or truly lets distant events share one inseparable story. 2015, 2 labs, one in Delft, another split between Vienna and the Canary Islands. They armed themselves with the fastest optics and the coldest crystals on Earth. In Delft, Diamond Lattice hosts single nitrogen vacancy centers. Each spin is entangled with a photon that races through optical fiber to a central station. In Spain, entangled photons leap from La Palma's mountain observatory across 143 kilometers of open sky to Tenerife. Random number generators, fed by quantum shot noise, choose detector settings after the particles are already in flight. High-efficiency superconducting sensors close the detection loophole. Spaced-out stations ensure choices are space-like separated, closing the locality loophole. When the counts are tallied, the CHSH score lands above 2.4. Decisively beyond the classical cap of 2, exactly where quantum theory predicts. Hidden variable realism, at least of the local kind, is out. No secret script, no subliminal handshake can explain statistics that demand a single shared draft across light years of potential separation. Einstein's worry remains. Spooky? Yes. But the universe votes with the data. Entanglement is woven into its fabric, and any deeper theory must carry the same non-local heartbeat. Entanglement does more than violate inequalities. It forms the backbone of quantum teleportation, transferring a state while leaving the particle behind. Alice and Bob share an entangled pair. Alice performs a joint Bell state measurement on her half and an unknown qubit she wishes to send. The act entangles history, collapsing Bob's distant qubit into a state related to the original by a known rotation. 2 classical bits race along fiber or satellite link. Bob applies the correcting twist, and the quantum message is restored. Original, destroyed, copy, reborn. No faster-than-light courier required. The first demonstration, 1997, Innsbruck, sent photon polarizations across a few meters. 2 decades later, China's Mischief satellite teleported qubits between ground stations that are 1,200 kilometers apart through the shimmer of the upper atmosphere. In labs, ions, NV centers, and superconducting circuits now teleport states between memory nodes. The essential move for a quantum repeater, and hence stretching fragile entanglement across continents, teleportation shifts focus from moving matter to moving information, hinting at networks where quantum keys distribute unbreakable security. Clock arrays sync with attosecond precision, and distant telescopes merge into planet-sized interferometers. All because pairs of particles once entangled behave like two ends of a sentence that cannot be split without losing meaning, no matter the gulf between. Think of a future internet whose backbone isn't copper or glass, but shared quantum drafts. In this network, entangled photon pairs are generated at central factories, buffered in quantum memories, cold atoms, rare earth crystals, superconducting resonators, then swapped node to node. Each swap entangles memories farther apart, stitching kilometers, then continents, into one non-classical web. Such a web does more than move qubits. Two widely separated atomic clocks, entangled rather than merely synced, can average away local noise. Ticking in tandem with precision, unattainable by classical links, long baseline telescopes, fed entangled photons, could interfere starlight collected on opposite sides of Earth, yielding images as sharp as a single mirror the planet's width. Entanglement also sharpens sensors. A ring of interferometers seeded with squeezed, entangled light already underpins the record sensitivity of LIGO and Virgo. Next-gen detectors dream of spotting primordial gravitational waves or the gentle murmur of dark matter fields. In biology labs, entangled two-photon microscopy reduces tissue damage while boosting contrast, letting researchers watch neuron circuits fire without frying delicate cells. Every application treats entanglement as currency difficult to mint, priceless once spent, and subject to strict accounting. Lose a single photon, and the ledger crumbles. Hence the race to build memories, repeaters, and error-resilient protocols before dicoherence can steal the coins. Entanglement comes with a jealous streak. If two qubits share maximal correlations, no third system can possess comparable knowledge about them, a rule called monogamy of entanglement. This exclusivity forms the bedrock of device-independent quantum key distribution. Alice and Bob perform random Bell test measurements on shared entangled pairs. If their statistics violate Bell inequalities by a healthy margin, physics itself certifies that no eavesdropper could hold a copy of their key. Any attempt to tap the line would sap correlations, lowering the score and sounding an alarm. Unlike classical cryptography, security here depends not on computational hardness, but on the impossibility of cloning entanglement. Monogamy also powers randomness expansion. Generate a short seed of trusted random bits, feed them into entanglement-based games that Bell violate, and you unlock long strings of certified unpredictable numbers critical for secure lotteries, simulations, and national security protocols. The same principle limits quantum networks. Entangled resources are precious because they cannot be freely shared. Engineers therefore invent entanglement distillation, purifying multiple noisy pairs into fewer, higher quality links through local operations and classical chat. In every protocol, the jealous nature of quantum correlation is both obstacle and shield. Constraining architectures, even as it guarantees privacy no classical system can match. Entanglement is not confined to lonely pairs. In condensed matter jungles, it links trillions of electrons into collective personalities. Peel back a sheet of graphene cooled near absolute zero, and you'll find currents twirling in fractional quantum Hall states, which are topological orders where anion quasiparticles carry fractions of an electron's charge. Their behavior is scripted by webs of multibody entanglement that wrap around holes in the material, like invisible laces, immune to local snags. Physicists quantify this hidden order with entanglement entropy. In ordinary matter, entropy scales with volume. In exotic phases, it hugs the area of a boundary, revealing long-range quantum stitching beneath. Tweak a parameter, magnetic field, disorder. Measurement rate and the system can undergo an entanglement phase transition. Not a change in symmetry or density, but in how information flows. Recent quantum circuit experiments have observed a critical point where random measurements sever enough links to tear a highly entangled state into disconnected islands. A novel kind of quantum percolation. Such many-body drafts might fuel fault-tolerant qubits built from non-abelian ions, where braiding world lines performs logic gates immune to microscopic noise. If successful, quantum computation will rely not on isolated pairs, but on seas of entanglement, arranged like intricate origami, robust, global, and strangely beautiful. What if the threads binding particles also stitch the cosmos? The ER equals EPR conjecture, proposed by Moldacena and Susskind, suggests that every entangled pair is connected by a microscopic, non-traversable wormhole. Stretch that thought. We've vast carpets of entanglement, and space-time geometry itself could emerge from the pattern. Tensor network models like Mera build holographic universes where each link is an entangled bond. Cut enough bonds and the simulated space pinches off, mimicking black hole horizons. In anti-de Sitter spacetime, the Rudikai-Yanagi formula equates the area of a minimal surface to entanglement entropy, turning geometry into bookkeeping for quantum information. Recent island calculations describing Hawking radiation entanglement recover the page curve, hinting that black holes do not destroy information. They release it through correlations woven across event horizons. Tabletop experiments with superconducting qubits have even simulated toy wormholes, teleporting quantum states via entanglement-assisted circuits that mirror gravitational dynamics in one spatial dimension. These ideas remain conjectural, but the takeaway is profound. Space-time might not be a stage, but a tapestry whose threads are entanglement itself. Alter the pattern, and geometry warps. Sever it, and space could crumble like a pulled sweater. Entanglement is fragile in the wild. Stray photons, vibrating lattice, cosmic rays. Each interaction siphons coherence, handing information to the environment and converting quantum poetry into classical prose. This is decoherence, the same relentless leak that saved Schrodinger's cat from eternal limbo. Quantum engineers respond with entanglement distillation, compressing many noisy pairs into fewer but purer links, and with error-correcting architectures that spread a logical qubit across hundreds of physical ones. Surface codes form two-dimensional quilts where any local tier can be sewn shut. Emerging LDPC codes promise similar protection with fewer stitches, yet there is balance. Absolute isolation kills usefulness. Quantum sensors need just enough coupling to read the world without drowning in it. The art is to negotiate a ceasefire in the tug of war, keep the drafts coherent long enough to compute, sense or communicate, then let them collapse when their story is told. Entanglement reveals a universe knitted together by invisible threads, but daily experience hides the weave. The culprit is noise, sunlight, air, thermal jiggle, constantly measuring, constantly collapsing, erecting the sturdy walls of classical cause and effect. Part 5, Decoherence. Why we don't notice will follow that noise, showing how environmental observers sculpt pointer states. Why macroscopic irreversibility blooms from reversible equations and how life leverages just enough quantum subtlety before surrendering to thermodynamic tide. We will explore quantum Darwinism, meet quantum error correctors, fighting entropy, and see how the same leaks that steal coherence give rise to the arrow of time. Entanglement has shown us the hidden webs. Decoherence will explain why those webs rarely sparkle in daylight, yet never fully disappear.